on.
We just got done talking about the plate movements across Earth's surface, and what happens at these plate boundaries or along fault lines is we experience earthquakes. And what an earthquake is just this rapid release of elastic energy. The elastic rebound theory tells us that as the stress builds up, what's going to happen is along the fault line, eventually the stress gets so great that it's going to snap and release that energy. But the pieces are going to spring back into their original form. They're not going to stay bent or curved. They're going to spring back into their original form. They're just going to be displaced from one another along that fault line. When it comes to earthquakes, we have three different types of waves. The two main waves are P waves and S waves. And P waves stand for primary waves. These are going to be the fastest moving waves. They travel through not only solids but liquids, so you can see them traveling through the mantle here. And then as they reach the outer core, what's going to happen is they just get deflected slightly when they enter. They're going to be deflected slightly again, but they are going to reach the complete opposite side of Earth from where they originate. S waves, or secondary waves, are slower moving and they can only travel through solids. So what happens when they reach the outer core is they just stop. If they do not make it through the mantle only, then they will not reach, and we will see no signs of S waves whatsoever on the other side of the world. When we look at these P and S waves, we take a look at a seismogram. And what a seismogram is you see the introduction or the arrival of first the P waves, then the needle will slow down because the vibration is going to reduce. Then the vibration starts back up again, this time being slightly larger, and that's going to be the arrival of the S waves. And not quite immediately following the S waves, but soon thereafter are surface waves. And surface waves are abbreviated as L waves. Surface waves are our most destructive. When we talk about the movement of these three waves, we talk about P waves traveling through both solids and liquids, and those are going to travel in a push-pull manner. If you think about a slinky, if you stretch that slinky out, push one end of it forward, you'll see the wave traveling through the slinky to the other end, eventually making its way all the way back. And that is how these P waves travel. S waves are going to travel in a snake-like pattern. If you were to take a rope, you hold it on one end, a friend on the other, and you snap your wrist up, it will send the wave up and down all the way through the rope and then making its way back. Surface waves travel along Earth's surface, and they travel in a wave-like motion. If you put a drop of water into a bucket of water, you see that ripple effect working its way from the center all the way out. And the same thing holds true from the location of where our surface waves originate from, the epicenter. The epicenter is the location on Earth's surface where we say we locate earthquakes. When we talk about earthquakes in the news and where they've occurred all around the world, we talk about a specific location on Earth's surface, or we talk about the epicenter. What actually happens is the earthquake originates somewhere below Earth's surface along the fault line. And the original, or the origin of the earthquake is at its focus. And the focus is directly below the epicenter underneath Earth's surface. How we come about to figuring out where the earthquake originates, because it's sending waves in all directions, and there are seismographs located throughout the entire world that are picking up the different vibrations on the seismogram, is we take a look at least three of the different seismographs, and we take a look at them on this time travel graph. So most of the time, the line is just going to, or the needle is going to be steady, not a whole lot of vibration going on. Then we take a look, eventually when the first wave hits, and again that is the P wave, and we look at the P wave then we also match it up with the S wave arrival time. To look at where specifically it occurred, or to figure out how far away that location is from the epicenter, what we do is we add a third line into the mix, and that is the S minus P arrival time. From there, we can drop straight down to tell us that a location is roughly 1,000 kilometers away from the earthquake's epicenter. What we can then do is take it from 3 different locations. We'll just call these points A, B, and C. And since we know that point A is roughly 1,000 kilometers from the epicenter, point B is going to be 2,000 kilometers from the epicenter, and point C crosses through at 3,000 kilometers from the epicenter. We look at the triangulation point, or right there. The reason that we can't use just 2 locations is because if we look again at points B and point C, we have 2 different points where the lines cross. And those are, if we have an actual map, could be thousands of miles or kilometers away from one another, and that is no help whatsoever in determining the location of an earthquake. So we use it the third point to bring in the exact point, or the triangulation mark, of where all 3 lines cross, and we know that specifically that earthquake crossed right there. Now we have 3 different scales when we measure earthquakes. The first is the most common that you know, and that's the Richter scale. And what the Richter scale is a scale of 1 to 10, and it's measuring the largest wave produced by the earthquake. Each level is an increase of 10 times larger than the previous. So a Richter scale of level 2 is 10 times larger than level 1. A 3 is 10 times larger than level 2. In all reality, though, this is not the most accurate. The most accurate way of measuring an earthquake is using the moment magnitude scale. And the moment magnitude scale is, once we find the exact location of the earthquake, scientists go out and go to the fault line, and they measure the displacement along that fault. They actually measure how much the Earth's surface has moved from its original location. And this is really easy when it comes to areas like farmland, and you can see the actual crop rows and just measure the displacement off that. It gets a little bit harder when you're just in an open grassland, for example. And then the third way that we measure earthquakes is the Mercalli Scale. And the Mercalli Scale is measuring damage. So this one isn't done for at least a couple days, if not longer, after the earthquake takes place, because it's based off of how much damage the earthquake actually produced. And different things that are going to determine how much damage occurs is things like the duration of the earthquake, how long it lasted, the intensity of the earthquake, the building materials that were used in that specific area. In more economically developed countries, we have more money, so we can put things like shock absorbers underneath our tall skyscrapers or tall buildings in areas that we know are prone to having earthquakes. In other areas, they don't have this luxury, and they build their buildings out of metal because it needs to be able to withstand the weights of the height, and what metal does, it just continues to carry out that vibration. In smaller buildings, we can use things like wood instead of the steel, and in areas that we know there's high traffic or a lot of roads, we can use rebar to support or to absorb the vibration going through the road, so that way they are not cracking as easily if it is just a low-scale earthquake.